Welcome to the last section in this unit. Congratulations, you've made it this far. I'm so impressed. Now, this is not going to be quite as difficult as the last few sections. We're talking about relative motion, and you've all recognized this in your life, but we're going to discuss it. Frame of reference is really important when we're talking about relative motion. The frame of reference that something is seen from may yield very different displacement or velocity for the object in motion. And you all recognize that if you think about the frame of reference of the plane. If you're looking at this from the point of view of the plane, as these parachuters are jumping out of the plane, they would appear to, say, the pilot in the plane itself to be moving at a very different velocity and direction as, say, the frame of reference of a person on the ground, or the frame of reference of some clouds. The frame of reference that you choose makes a big difference on how the motion is described. These are all examples of that fact. People riding on the moving sidewalk. The frame of reference could be from another person on the moving sidewalk, or the frame of reference could be from someone standing still on the other side of the sidewalk, or someone walking on the other side of the sidewalk. How about a boat that is traveling on a river that is moving, or someone who is walking or leaping or jumping on a moving train? What is the frame of reference that you're going to use to describe that motion? Another example would be cars going at different speeds. Here's a slower car and a faster car. The frame of reference definitely matters. This is just a fun little illustration showing this point. Let's say we have a house and a tornado, or a storm, a hurricane, whatever you want to call it. If we choose, and we have a car here as well. Let's say we choose the house as our reference point. The car will appear to be traveling 10 kilometers per hour west. Here's initial, and here's after 1 hour. What is happening? The car appears to have traveled 10 kilometers per hour west, and the storm appears to have traveled 20 kilometers per hour west. What if we choose the car as the reference point? In that case, the house appears to travel 10 kilometers per hour east, and the storm appears to travel 10 kilometers per hour west instead of the 20 as before. Very different. Even though these are the same. If you look at, this is the house as the reference point, this is the car as the reference point. After 1 hour, the total displacements of everything are the same. The choice of reference point, though, definitely affects how you describe the motion. Let's look at this example of a fast car and a slow car. We're going to call the fast car little f, and we're going to call the slow car little s. And we're going to represent something called, with respect to Earth, as a little e. And I'm going to explain some of my notations here. Let's say the fast car, the velocity of the fast car with respect to Earth is a positive 90 kilometers per hour. We're going to determine just arbitrarily that north is positive. So it's a positive 90 kilometers per hour north. Let's say the velocity of the slow car with respect to Earth is positive 80 kilometers per hour. So it's going north as well. We can know those things. Their speedometer tells us that as well. How can we find the velocity of the fast car with respect to the slow car? We would represent that as velocity of the fast car with respect to the slow car. In order to do that, we can find the velocity of the fast car with respect to the slow car by adding two vectors in which it begins with the fast car and ends with the slow car. So we get fast car with respect to the slow car. How do we do that? We can find the velocity of the fast car with respect to Earth. We could find the velocity of Earth with respect to the slow car. Wow, that seems strange, doesn't it? How are we going to do that? If you'll notice, velocity of Earth with respect to the slow car is just the inverse of the velocity of the slow car with respect to Earth. Therefore, we can substitute this idea. We can say the velocity of the fast car with respect to the slow car is equal to the velocity of the fast car with respect to Earth minus the velocity of the slow car with respect to Earth. That will give us our answer. And we can do that because we know the velocity of the fast car with respect to Earth is plus 90 kilometers per hour. We know the velocity of the slow car with respect to Earth is 80 kilometers per hour. So 90 minus 80 equals positive 10. So the occupants of that slow car are perceiving that the fast car is moving at 10 kilometers per hour north. So as they're sitting in this little slow car, they look over and it appears that that fast car is going 10 kilometers per hour north. Now this is a really simple problem, and you could do this in your head, but I want to walk you through the idea behind it because problems can get more complex than this. Okay, let's do an example. A plane flies northeast at an airspeed of 563.0 kilometers per hour. This is relative to the wind. I just realized I really should have flipped that plane around so it was appearing to fly northeast rather than northwest. Anyway, a 48.0 kilometers per hour wind is blowing to the southeast. What is the plane's velocity relative to the ground? Well, the first thing we have to do is draw a picture, right? Right. So let's draw a picture, find out what we know. I am going to do this one particular way. You are welcome to turn the XY axis or turn everything around. You are welcome to have northeast pointing straight up, in which case your diagram would look like this and then like this. You're welcome to do that and just change the coordinates. I am going to do it a different way. The first leg of my journey is going to take me northeast, and it will be the velocity of the plane relative to the wind. Plane relative to the wind, and this will be northeast. I'm basing that on just the idea of the compass rose being north, south, east, and west. Now the second vector I need to consider is the velocity of the wind relative to Earth. Velocity of the wind relative to Earth is 48.0 kilometers per hour directly to the southeast. Now, it's also important to notice that in this case, this will be a right angle right there. So we do know that. We also know that this angle is going to be 45 degrees. And we don't know, right here, we don't know if this goes all the way back to the original location or not. So we're going to have to assume something here, if I can draw this. Here's my resultant vector, and I have some different angles here. There's this angle right here between the pink line and my resultant vector. And that is the one that I will be using to determine some of my values here in a minute. After the fact, we can look at which angle we really want to address here. But for now, this will be the angle that I'm going to want to look at. If I end up in my problem, now this could happen, I may end up with a theta, an angle that is negative. If that is the case, then I know that my resultant vector, will actually have to be down below here, and this line will extend down there. I'm going to just make an assumption that it will be positive. But if I get a negative number, a negative value, I'm going to have to extend that resultant vector in a different quadrant. So now I wrote down all my unknowns. I went ahead and filled in this resultant is the velocity of the plane to the Earth. And it is unknown. We don't know that. We do know these two values. So because we have a right triangle right here, we can use the Pythagorean theorem to determine the magnitude of the velocity of the plane to the Earth. So I can set that problem up like this. Velocity of the plane to the Earth squared equals the velocity of the plane to the wind squared plus the velocity of the wind to the Earth squared. It's just the Pythagorean theorem here. This squared plus this squared equals that squared. If I substitute values in, I can substitute my 48.0 into here, my 563.0 kilometers per hour here, and that will give me, and I take the square root of all of that and the square root of this, I will determine what the velocity of the plane to the Earth. And that will be, the velocity of the plane to the Earth will be 565 kilometers per hour. And you'll notice that I know the magnitude, but I don't know the direction yet. So what do you suppose we're going to use to find the direction? And if you guessed the tangent function, you are right. Okay, so here is our equation. Remember the tangent of theta equals opposite over adjacent. I just abbreviated those. The opposite would be the velocity of the wind to the Earth, and the adjacent is velocity of plane to Earth. So rearranging the equation for theta, theta is just the inverse tangent of the velocity of wind to Earth, which is this, and divided by the velocity of the plane to Earth, which is that number. I end up with 4.87 degrees. What does that mean? Well, if we look at our diagram, 4.87 degrees is theta right here between the pink line and the blue line. That's our theta. That means I'm 4.87 degrees east of northeast, if that's directly northeast. Remember, northeast is exactly 45 degrees from north and 45 degrees from east. It's right in the middle. Therefore, all we need to do is say 45 degrees minus 4.87, and that gives us the difference. If we take all of this and say 45 degrees and we subtract this piece, the 4.87 from it, we end up with 40.1 degrees. That number tells us basically what, it's hard to write in here, it tells us this angle right in there. So 40.1 degrees would tell us the angle north of east. That's north of east. And that's a more descriptive, a better way of writing it rather than 4.87 degrees east of northeast. But either answer is correct. Finally, just check, double check, verify, make sure this answer makes sense. Here are some advanced ideas. There is a section in your textbook that discusses Einstein's relativistic addition of velocities. It's really interesting, really exciting, talking about the constancy of the speed of light. And that's the little joke here, c being the speed limit. The speed of light is the speed limit. Read that. See if you can come up with answers to one of these ideas here, and I look forward to seeing what you come up with in class.